So in this portion, we are going to look at a couple of sample problems. The first sample problem concerns planar incompressible flow, where the form of the velocity is given to you. It's a two-dimensional flow, and this is the first term and this is the second. What you're being asked is to determine the stream function for this flow field if psi at 0, 0 equal to 0. Okay, so this is one more condition that is provided. The second question is concerns 2 points A and B which are provided, and it's 1, 0 and 0, 1, and you are being asked to figure out the volumetric flow rate across the line AB. Now here, so the first thing what you will do is you have to find the stream function. So ux is already provided, so del psi del y, you already know of this form. You do the integration, and then when you do this integration, this is the partial derivative of y. So when you integrate, you can have a function of x that is undetermined. Right? So the constant of integration can be a function of x and not just a normal constant. It will not involve y, but it can be a function of x. Similarly, when you do uy, which is already known to you, when you integrate psi from this particular equation, you will have a constant of y term here, such that both f and g here are unknown functions. So the two integrations lead you to two separate forms, and you can compare these two different forms, and by comparison you can establish that the g of y is equal to minus 2/3 y cube plus some constant, and this constant is a constant devoid of x or y. So this is a general constant. Similarly, if we comparison, you can easily determine that f of x is equal to another constant. So the stream function you can easily build from here, and once you compare the two functions, you get to this, then you are now able to write it as 2x square plus 1 by 2x square y minus 1 by 3rd y cube plus constant, and this constant has to be determined. So you are already given that if at psi equal to 0 is equal to 0, so c equal to 0, so this is the stream function form. The volumetric flow rate, when you are asked about AB, you only have to figure out the volumetric flow rate. Basically, imagine two streamlines passing through, one through 1, 0 and another through 0, 1. Now AB will, whatever the flux through AB will be just the difference of the stream functions. Okay, this is something you can, if you want to prove for yourself more rigorously, you can, but this is simply the two stream functions evaluated at these two places. So the answer is 2 by 3. This is the second problem that I had asked, and I had, when we were discussing stream functions and building block stream functions, I had given this problem to you and I had asked you to solve for it. So just to repeat, you have two ones, one is a source and one is a sink, both located at A, away from the origin. One is on the right side, another is on the left hand side, and both are located at y equal to 0. Okay, so this is y and this is x. In terms of the r theta system, you take any point which is at r theta, and this, with the first case, will subtend an angle theta 1, and this radius is r1. With the second one, it will subtend r2 theta 2. Now by superposition, you can say that the two, and we had already written this part, that the superposed stream function for this combined case is m by 2 pi theta 2 minus theta 1. Now in this case, what you need to do is you take the tan of, so you bring m by 2 pi onto this side, and then you take the tan of both sides. Okay, so then you get, so take the tan of this is taking the tan of theta 2 minus theta 1. This, from trigonometric identities, you will end up with this. Now you have to find out what tan theta 1 is. Tan theta 1, given the geometry, should be of this form. Please check that. tan theta 2 from geometry should be of this form. The plus a minus a changes to plus a here. So please check if I have done this correctly. And then you have tan 2 pi psi by m is equal to this function here. If you simplify this, you end up getting this function. Again, you should double check. From here, you can easily get psi as m by 2 pi tan inverse of this quantity. I have drawn, and this is not the best sketch, but this is how the stream functions would look like if you have if you were to draw them. Okay, so the flow starts from this source, ends up at the sink. Similarly, all these streamlines, but there will be some streamlines which are sort of going off to a very, very large distance. An interesting problem to look at here is a very special case, okay, and special case. And that special case is of a doublet. Okay. Doublet is created when you let so a doublet is formed by superposing, let's say, a source at a sink of equal strength separated by an infinitesimally small distance, which means that for a doublet I need to get, that is, a needs to tend to 0. If that happens, your limit of a tending to 0 for psi becomes m by 2 pi. So if I look at this equation here, you will have the m by 2 pi. Now when you take the condition of a being very small, so then this number becomes a very, very small quantity. Okay, then the tangent, the tan inverse, basically tan inverse theta is basically theta in that case. So you can write this as, minus 2ar sine theta r square minus a square. Now if you do let a tends to 0, keeping m finite, this entire term will end up going to 0, because this is r square, here you have a, so this entire term ends up 0. So psi will end up to be 0 if you let a tend to 0, and this is sort of a trivial situation. So you create a case where, consider a case where when a tends to 0, m tends to infinity such that, okay, now m tends to infinity is not enough, so you have to tell how it is tending to infinity. So then if we say that such that m by 2, this ma by 2 pi equal to some constant k, then what happens? Then your psi approaches, so the first thing is k, and you will have a 2 sine theta by r. Right? So this becomes a doublet. Okay. And so this is a question I'm going to leave you with. What do streamlines for such a doublet look like? This is something you can easily maybe use MATLAB to plot and check for yourself how the streamlines look like. So please do that and check for yourself. Okay, so I'm going to stop here. Okay, thanks.